Welcome to Differential Equations. In this class, we're going to talk about a specific type of equation, an equation that involves differentials. In order to understand what an equation involving differentials is, we need to understand what is a differential. And what is it related to? Well, a differential is the instantaneous rate of change of a quantity. And usually we work with ratios of differentials. A ratio of differentials is a derivative, which you know from Calculus 1. When we write dy dx, what we're doing is we are saying the rate of change of y with respect to the rate of change of x. So the formal definition, if you remember, is something like this. This is the forwards difference, f of x plus delta x minus f of x. That's the change in y, the change in the value y, or the change in the function f, if y is equal to f of x, over the change in x. And that, of course, is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. That's what we mean by the derivative. So when we talk about a partial or a differential like delta x, you can think of that roughly as the limit as delta x approaches 0 of delta x itself. And similarly with y or df, you can think of as the limit as delta x approaches 0 of y of x plus delta x minus y of x. If x is the independent variable and y is the dependent variable. So just keep that sort of in the back of your mind. We're going to be setting up equations that relate these differentials and working with them. An equation is a relationship between quantities usually expressed with symbols. So we've had probably at this point several different types of equations that we've worked with. Maybe we've never actually separated them out before. Logical equations involve logical variables In other words, they take on the value true or false. And represent statements. And there's really two types of symbolic logic equations. You have predicate logic, and you just have standard formal logic. In predicate logic, we use functional notation to denote statements. So, for instance, if X is defined as a boy and G of an argument is defined as the argument is Mel, then the predicate G of X would evaluate to true, right? If we were instead to say A is unknown and G of A is false, then we know logically that A is not Mel. And we can deduce possible solutions for what A is. Okay, so that's one type of equation and one type of solving an equation, a logical equation. And they can be much more complex than this and involve multiple variables. We've also seen algebraic equations. And these types of equations usually result in a solution that is a number, a value. So, for instance, in algebra, you might have solved problems like this. Okay? How would I go about solving something like this? I would square both sides. I would subtract L and subtract 2 from both sides. You could use the quadratic formula. Or you could just kind of realize by looking at this that this is the same thing as L minus 2, L plus 1 equals 0. And note that this occurs when either L minus 2 is equal to 0 or L plus 1 is equal to 0, and solve for L to find that L is equal to 2 or L is equal to minus 1. So those are the two solutions to this, this algebraic equation. Another type of equation that you may have worked with is a trigonometric equation. Again, a type of algebraic equation, really, where we have, for instance, trigonometric relationships between variables and values that result in solutions that are, let me do it this way instead, that are still numbers. Sometimes sets of numbers satisfy equations. For instance, if we had sine of theta equals 1/2, then we would solve this by taking the inverse sine of 1/2. And if you remember your trigonometry at all, when I have a right triangle and I have an angle in that right triangle, the sine of that angle is equal to the opposite side divided by the hypotenuse of the triangle. So this would be A over H, right? And if we're letting this be 1/2, then we have a triangle where A is 1, H is 2, and we're looking for this angle. Now, if you remember your unit circle, that angle is actually pi over 6, but recall that we're also interested in all multiples of this angle, because if we consider the angle theta, we can achieve the same angle by adding, this is theta plus 2 pi, and then this would be theta plus 4 pi, and so on. So all integer multiples of 2 pi. So to be entirely precise here, we would say theta is an element of the set pi over 6 plus 2 n pi, where n is a natural number. Okay, the final type we'll talk about, you learned in calculus, and these are still algebraic equations. They simply involve calculus operations. So an example of one of these would be finding y such that y is equal to the integral of x squared dx. Y, therefore, is equal to 1/3 x cubed evaluated between x is 0 and x is 1, which is just 1/3. So again, a value. All three of these are types of algebraic equations where the solution is a value. The previous type of equation is a logical equation where the solution is a set of objects or items which satisfy a logical expression. Very much so related to our algebraic equations. The items are just restricted to be numbers. A differential equation relates differentials of quantities. You're not going to find a number. You're not looking for numbers. You're looking for equations, you could say, or really a better terminology is functions. You're looking for functions of variables or dependent variables. In other words, we must find the function which satisfies the differential equation. Example. Here, your unknown wouldn't be 5. It's going to be a function. Y of t equals 3e to the 2t, for instance. That's a function of t. A quick history of differential equations. Always worth studying why we consider these things a field in the first place. The history goes like this. In 1676, Newton wrote to Leibniz, he was concerned with two objects that he had named, fluxions, which you can think of as time derivatives, and fluents, which are what has come to be known as differential equations. Functions whose rate of change is unknown. And essentially he posed the question, if I tell you how fast something is changing, at every moment in time, can you reconstruct the thing itself? And 350 years later, this is still the heart of differential equations. Definition. Ordinary differential equation. One, must have an independent variable. Usually we use x and t in this class. Two, it involves an unknown function of x and t. And three, usually we'll use y of x, f of t, or variations of those. And three, one or more ordinary derivatives of the function. Those are the things that an ODE involves. So ordinary as opposed to partial just means there is only one independent variable. So here's an example. Y prime equals 2y. Y is a function. Okay. So that's what this little prime tells you. If this was just y equals 2y, we might assume this is algebraic. Right? And here we would solve this by subtracting y from both sides, and we would find the solution to be y equals 0. It's the only solution for this equation. And this equation, this differential equation, maybe more clear way to write it would be y prime of t is equal to 2y of t. dy of t dt equals 2y of t. Or maybe the clearest way of all, dy equals 2y dt. Here's an example, a practical example. Rabbits on an island. Suppose we place 10 rabbits on an island and the number of rabbits being produced on the island will be changing in relation to the number of rabbits on the island. Population dynamics are a really important example of differential equations. So in this situation, one potential way to describe this would be as follows, symbolically. Y of t is the population size at time t, and we may relate y prime of t to this population size in the following way. In other words, the rate of change of the population with respect to time is 2 times the size of the population at that time. This is saying population continuously doubles. The solution turns out to be y of t is equal to 10e to the 2t. And this is how many rabbits there are at time t. In 1798, a little bit of dyslexia there, 1798, Thomas Malthus argued that human populations would outstrip their food supply. Luckily, we didn't do that. We're all still eating. Probably some of us are eating too much, like me. 3 perspectives that will follow us through the course on differential equations are as follows. The theoretical, of course, we want to be rigorous and do proofs, have definitions, generalizations, extensions, things that we can theorize about, theorems that we can come up with and prove mathematically through thought experiments. The computational angle, the differential equation systems that are useful nowadays are usually so large that the right tool for the job is not a human brain, but a computer, which the human brain invented. So the computational angle in this class we'll be using Julia, since that's sort of state of the art right now. No telling what it'll be in a year, but right now the differential equations library in Julia is pretty good, so we'll be using it. And the applied angle. I want to be sure to give you applications, because these differential equations are used to usually describe physical systems, and the physicists should not have a handhold on those systems. We should be able to, as mathematicians, describe physical systems that we observe in the real world as well. So one quick note. We have been talking about ODEs as opposed to PDEs. These are ordinary. These are partial. In an ordinary, there is one independent variable, and we're concerned with a function of that. In partial differential equations, there are many independent variables. That's the main difference. An example of an ordinary differential equation that we've been working with on the opposite side is this. This is actually the equation which is used to describe radioactive decay. The rate of change of y with respect to t is equal to the opposite of some decay constant k times the amount of radioactive material at that point in time. The heat equation is a partial differential equation. du dt del t is equal to k times del squared u del x squared. The rate of change of heat with respect to time is a constant times the second derivative of the rate of the rate of change of the rate of change of heat with respect to distance from the source. So a partial differential equation is a lot harder to solve than an ordinary differential equation, but both are equations which involve differentials. In this class, we'll specifically focus on ordinary differential equations. We can classify differential equations in 3 dimensions. O-law. Every time you see a differential equation, you should tell it O-law. You should, 1, look at the order. That's the highest derivative. 2, the linearity. This is, does it contain powers of the dependent variable? Or the function. That's another word for a dependent variable. 3, autonomy. This is maybe the hardest one for students to see, but it's not so bad. Does the independent variable appear on the right-hand side, outside the function? So we'll classify a few of these and it'll become clear. Let's do order first. Here's a differential equation, y prime equals y. The highest dimension is the first, so this is a first order differential equation. The differential equation y double prime plus y prime equals 0 has dimension 2. So this is an order 2 differential equation. Y triple prime equals ty prime minus y. 3, third order. Y 4 plus y double prime minus 3y equals sine of t. That would be a fourth order. So identifying the order, it's fairly easy. You just find the highest derivative that is being taken. Now one quick note that'll make more sense in a minute. First order require one initial value for the particular solution. Second require 2, third require 3, and so on. So for instance, for the first order to get a particular equation, you would need to know, for instance, something like this, y of 0 equals 3. For the second one, you would need to know something like this, y of 0 equals 3, and y prime of 0 equals 4, say. And for the third order, you would need y of 0 equals a, y prime of 0 equals b, and y double prime of 0 equals c to solve for the equation. Second criteria, linearity. The ODE is linear if the function y appears only to the first power and there are no multiplications that occur of the function y with any of its derivatives. So, linear if y only to first power and no multiples of y with its derivatives. Okay, so let's do a few examples. Y prime plus 2y equals t. Linear or not? Yeah, that's linear. Y prime equals t times y. Linear or not? Yeah. Y prime plus t squared y equals e to the t sine of t squared. Linear? And why? Yes. Now, y double prime plus y squared equals 0. Linear? No. Y prime equals the square root of y. Linear? No. Y prime squared plus y equals 0. Linear? Again, no. And y times y prime equals 1. This also is non-linear. So only look at y. Inspect for products of y. If you have them, then it's nonlinear. If you don't, then it's linear. Linearity basically means that the differential equation is well behaved and we don't have too much trouble with it. But it's a great divide when things are nonlinear, and this is basically everything else. You know, a linear differential equation is probably not a real thing that actually exists. And nonlinear are much harder to solve. And we have a lot of different tools that we use to make them look as linear as possible. So the last criteria that we classify the differential equation on is its autonomy. If f well, let's write this a slightly different way. Let's say this. Let y prime of t be equal to f of y. The rate of change of y with respect to t is only a function of y. That's what it means to be autonomous. If you have a situation like this, doesn't even have to be so. Then the rate of change depends on the clock too. Right, it depends on t as well as y. That's not autonomous. So let's do some examples, and then there's a pretty good illustration of this with a thermostat. So for example, here is a differential equation. Is this autonomous? Well, it doesn't appear to depend on the independent variable. So, yes. Y prime equals y squared, also autonomous. Y prime equals 3y minus 7, also autonomous. Y prime equals t times y, no, if t is the independent variable. Y prime equals y squared times sine of t, also no. Why does autonomy matter? Well, if y prime equals f of y is autonomous, then the slope at that point depends only on the height of the function y of t, and not on t, the independent variable, or the horizontal position. In other words, every point is at the same height. Every point that is at the same height will have the same slope. The direction field, which we'll talk about in a minute, is identical in every column. And solutions are what's known as time shift invariant. Y of t is a solution. So is y of t plus c for all C then. Direction fields are a way to visualize the general solution of a differential equation. Before we talk about those, though, I want to give you an illustration. A thermostat doesn't depend on time of day, only on the current temperature, which in turn depends on time. But a programmable thermostat that I can set to 70 degrees at 10 a.m. depends on current temperature and time. And therefore, this is autonomous. This is non-autonomous. Let's have 3 quick examples and do a full classification. Y prime equals the opposite of 2y plus 5. Order, linearity, autonomy. Hola. First order, linear, autonomous. 2. Y prime equals y squared minus t. First order, nonlinear, non-autonomous. 3. Y triple prime plus t times y is equal to e to the t. Third order, linear, non-autonomous. Let's talk about direction fields. Also sometimes called slope fields. If we have a differential equation like this, y prime equals f of t comma y, again, non-autonomous, because it involves both the independent variable and the dependent variable. We know the slope of the solution at each point t comma y in the plane. That is f of t y, right? This equation says the slope of the function y is equal to this function of t and y. So the slope at each point ty is f of t and y. A direction field is like a compass. If you're lost in the foggy woods and you can't look up and see the sky to determine where you're going, but you can look down to see your compass and it can tell you where you're going, you can see at that point in time where the compass is pointing you to go and find your way out without having a full picture of what's actually going on. The direction field is very similar to this. It tells you generally the way that the function is behaving. And they look something like this. A grid with a bunch of different slope values, and they don't have to be even or not. The way you draw these, one is you choose a grid. Usually integers. Doesn't have to be, just a countable grid. 2, at each point, compute f of y comma t. 3, draw a short line segment with that slope. And then your direction field is done at that point. But 4, you should not really create one if you're not going to look at it for patterns. What's the point? Example. Y prime equals y. The slope of the function y is equal to the function value. Our grid t comma y may be 0 comma 2, and the slope at that point is what? 2. Our grid point may be 1 comma 2. The slope at that point, again, 2. Doesn't matter what the position horizontally is, because this is non-autonomous. This is an autonomous equation. We may have 0 comma 1. Slope is 1. And in general, if we just draw the thing, 1, 2, 3, 4, this is t, this is y. When y is 0, we just have a bunch of horizontal lines. When y is 1, we have a bunch of lines with slope 1. When y is 2, our slope is 2. And 3, the slope is 3, and it just increases. So looking at this direction field, we can note a few things about the function. Y equals 0 is an equilibrium. If it ever gets into the point where it's at y is 0, the slope is 0, so it'll never change. It'll always be 0. 2, above y, if it's above y at all, the slope starts out small and then starts getting bigger, 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 bigger. So slope increases. This is exponential growth. And 3, below y equals 0, the slope decreases. This is exponential decay. Sometimes this is called just exponential decay, yeah. For the equilibrium at y equals 0 is unstable. Right, it's like a ball sitting at the top of the hill. If you push it a little bit in either direction, if you go up a little bit off 0 or down a little bit off 0, then you're gonna just increase in speed and keep going. So that's what we mean by stable and unstable equilibria. It turns out for this differential equation that the general solution, which we'll study later why this is c e to the t. When c equals 0, we have equilibrium. When c is greater than 0, we have growth. And when c is less than 0, we have decay. So Volhorst in 1838, in response to the Malthus claim that the rate of change of the population was directly proportional to the size of the population, proposed the differential equation governed by the carrying capacity of the environment. This K here is the carrying capacity. Right, so the idea is if an environment can support 100 people, then K is 100. And as y approaches 100, this term 1 minus y over 100 approaches 0. So as the size of the population, current pop size, as the current population size increases to the carrying capacity, the rate of change goes to 0. Because this factor is multiplied. So the resulting S-shaped curve the S-shaped curve is the logistic curve and also called a sigmoid. In the case of R equals 1 and K equals 1, Y prime equals Y times 1 minus Y. Let's read the direction field without solving this differential equation. Let's consider different regions. Y is greater than 1. Y is between 0 and 1. Y is equal to 1. Y is equal to 0. And y is less than 0. Okay, we're going to think about the sign of y. The sign of 1 minus y. And the sign of y times 1 minus y. Okay, If y is greater than 1, then the sign is obviously positive. The sign of 1 minus y is negative, and the sign of y times 1 minus y is negative. If y is between 0 and 1, the sign of y is obviously positive. The sign of 1 minus y is positive. And the sign of y times 1 minus y is also positive. If y is equal to 1, the sign of y is positive. The sign of 1 minus y is 0. There's no sign. And the sign of the resulting product, therefore, is also 0. There's no sign. If y is 0, the sign of y is 0. The sign of 1 minus y is positive. And the sign of y times 1 minus y is also 0. If y is less than 0, the sign of y is negative. The sign of 1 minus y is positive. And the sign of y times 1 minus y is therefore negative. So this actually tells us a lot about the function y without us even knowing what it is. 1, there's 2 equilibria. What are they? 0 and 1. Right? Y equals 0 is one of them, and y equals 1 is the other one. The y equals 0 equilibria is unstable. Why? Well, let's look at it. If y is equal to 0, then the sign of the derivative is 0, so it's not changing. So we're at an equilibrium. We're either at a stable equilibrium or an unstable equilibrium. If we're at a stable equilibrium, any little perturbation off of the equilibrium will just cause us to roll back down into the equilibrium. If we're in an unstable equilibrium, any little perturbation off of that equilibrium will cause us to roll far away from that equilibrium. So y equals 0 is an unstable equilibrium, because when y is greater than 0, the sign is positive. And when y is less than 0, the sign of the derivative is negative. So the thing goes away from 0. The y equals 1 equilibrium, on the other hand, is stable. If y is just above 1, then the sign of the derivative is negative. And if y is just less than 1, then the sign of the derivative is positive. So it's being pushed into that equilibrium. And solutions starting between 0 and 1. Trace the logistic curve, the sigmoid. They have a slow start. They increase in speed to 1, then slow down. They look like this. Okay. Solutions and initial value problems. Definition 4.1. The solution of a differential equation, an ordinary differential equation, y prime equals f of t comma y, on an interval I is y of t defined on that interval. Such that y prime of t equals our f of t comma y of t for all t in that interval, t in the interval. For example, we may claim that y of t equals 3e to the 2t is a solution of y prime equals 2y. The left-hand side, y prime of t equals d dt of this function, 3e to the 2t, which is, by chain rule, 6e to the 2t. And the right-hand side of this is 2y of t, which is 2 times 3e to the 2t, which is 6e to the 2t. So those two are consistent. You can always check your work this way. The general solution of a differential equation is written with an arbitrary constant c, usually, or k sometimes. And it contains all particular solutions. Right, so a general solution would be ce to the 2t, something like that. And this describes a family of particular solutions. One of them is 3e to the 2t. One of them is pi e to the 2t. One of them is I to the e times e to the 2t. One of them is the golden ratio phi times e to the 2t. Those are all members of the family, and there's many more. It's an infinite family, in fact. By plugging in an initial condition, we can solve for C, usually. So, for example, say y prime equals f of t comma y. So non-autonomous y of t naught equals y naught. That's what we mean by an initial value problem. So we may be given this differential equation, y prime equals 2y, and this initial value, y of 0 equals 5. Then we would solve the differential equation for a general solution by integrating and we get y of t equals c e to the 2t. You'll see that more formally next time, but for now, that is the general solution. And 2, we then take our initial value, and this is equal to c e to the 2 times 0, which is c, which means that c is just 5 in this case. So our particular solution is 5e to the 2t. Okay, I want to talk about a danger now called finite time blowup. The finite time blowup, this is a warning to you, is something that occurs with nonlinear differential equations. So consider the differential equation y prime equals y squared with the initial condition y of 0 is 1. It looks similar to the differential equation y prime equals y, but there are some major differences with regards to how it is solved. So if we take our differential equation that we're interested in working with, and we write out the differentials, that's usually a good thing to do when you're working with a differential equation. We can rearrange it, divide both sides by y squared, and then multiply both sides by the differential of time. And we can now rewrite this as this and integrate both sides. And the integral of this is actually minus 1 over y plus our constant. And the integral of this is t plus our constant. I'm going to let c be equal to c2 minus c1. So we have minus 1 over y is equal to t plus c. And y, therefore, is 1 over the opposite of 1 over t plus c. Now, apply the initial condition. The initial condition was y of 0 is equal to 1. And we find that 1 is equal to the opposite of 1 over 0 plus c, which means that c is equal to minus 1. And therefore, y of t is equal to the opposite of 1 over t minus 1, which is 1 over 1 minus t. And some of you may have seen this before. This is the witch of Agnesy. So the finite time blowup that occurs with the witch of Agnesy is like this. Consider t, then consider y of t is 1 over 1 minus t. At t equals 0, t equals 0.5, t equals 0.9, t equals 0.99, up to 1. When t is 0, we just have 1. When t is 0.5, we have 2 when t is 0.9, we have 10 when it's 0.99, we have 100, and this approaches infinity. It's undefined. This is an infinite time blow-up, is a finite time blow-up. Because it goes to infinity at time equals 1. So, realistically, when we talk about these things, the finite time blow-up is a type of occurrence which limits the effective interval. What I mean by that will become clear. The maximal interval is negative infinity up to 1, right, for this function. Not all the reals. So it's problematic. Let's consider a few things. Compare these two. Y prime equals y and y prime equals y squared. This is linear. This is nonlinear. The general solution here is c e to the t. The general solution here is the opposite of 1 over t plus c. The particular solution at y of 0 equals 1 is e to the t. The particular solution here is 1 over 1 minus t. The growth is exponential. The growth is faster than exponential. Does it converge? Does it reach infinity? Yeah, as t goes to infinity, and yes, at t equals 1. Does it exist for all t? Yes and no. The equilibrium point. Zero. Maximal interval. Goes from negative infinity up to infinity, and from negative infinity up to 1. So that's a quick comparison of those. And that is a pretty good place for us to go ahead and end this video. So read the notes below, work through the problems, reach out to me if you have questions, and I'll see you in the next